Okay, so what we're going to do today is we're going to move on to chapter 9.5. So chapter 9, section 5, which is equivalence relations. So in the previous lecture, we talked a lot about relations. We talked about um, symmetric, transitive, and reflexive relations. We talked about composing relations, unions of relations on sets. And now finally we get to probably the most important use of relations in this class, which is going to be an equivalence relation. And this will be pretty familiar. So definition, a relation R on a set A. And remember, a relation R on a set A means that it's a subset of A cross A. So over to the side, R is a subset of A cross A. Is an equivalence relation if it is a symmetric, reflexive, and transitive. So just for bullet points, if it is symmetric, that means A, B in R implies B, A in R. So you switch the order of the factors in your pair. Reflexive means that A is in R for all A in A, and then transitivity is if A, B is in R and B, C is in R, that implies that A, C is in R. Okay, just some review. And then as another definition, two elements, A and B of A, which are related by an equivalence relation, are said to be equivalent. Equivalent under that relation, and we can denote that by A tilde B R. This R subscript is saying these are equivalent under the relation R, but when the relation R is specified, or if we're dealing with only one relation R, then we can just write A is equivalent to B like this. Okay, and what I want to kind of take a moment to glance at is to say that if like the notation or the nomenclature of an equivalence relation is trying to say that we're setting up some equivalence along on some set. And so if we want to consider a bunch of elements to be equivalent, then these three properties are very reasonable ones to ask. The reflexivity is saying that A should be equivalent to A. So you shouldn't be able to distinguish between A and itself. Moreover, if A is equivalent to B, then B should also be equivalent to A. You shouldn't have an order in your relation if they're trying to be equivalent. And lastly, if A and B are equivalent and B and C are equivalent, then you would expect that A and C are equivalent or indistinguishable perhaps from the perspective of the relation. Now what I want to introduce is a bunch of examples which are kind of non-examples to show you just a bunch of different relations that are close to being equivalence relations or maybe not so close that involve these three properties. And they show you that interesting relations appear when you take any subset of these three. So examples. So first I'm going to take the relation on R. So this is going to be A, B inside R squared such that A is less than B. Okay, and up here I'm going to have a bunch of checkboxes. So this is for symmetric, reflexive, and transitive. So this relation is certainly not symmetric because if A is less than B, then B is not less than A. And remember, symmetric says for every time that I have A and B in there, then BA is in there. In fact, in this case, if I have AB, I never have BA. So it's definitely not symmetric. It's also not reflexive because A is not less than A. But it is transitive because if A is less than B and B is less than C, then A is less than C. So something that is transitive but not reflexive and not symmetric is one example of that is the less than kind of ordering. An easy way to add in one of these properties is to take A, B in R squared such that A is less than or equal to B. Still not symmetric because there exist examples where A is less than or equal to B, but B is not less than or equal to A, right? For instance, 1, 2. 1, 2 is in here, but 2, 1 is not in here because 2 is not less than or equal to 1. But it is reflexive because every number is less than or equal to itself, right? Pick any real number. Is it like, I don't know, pi? Is pi less than or equal to pi? Yeah. So this one is reflexive and it's transitive for the same reason. Okay. Um, Now let's do some more kind of interesting ones. And I try to, there are real life examples of all of these, and I try to do kind of real life examples as often as possible. So let's do A and B in the set of people squared, such that A and B work at the same company. Okay, so let's see what is going on here. Is this symmetric? If A works at the same company as B, does B work at the same company as A? Yes, it's symmetric. Is it reflexive? Does A always work at the same company as A? Not if you're looking at the set of all people, right? There are a number of people who don't work or who are retired, right? Things like that. So there are plenty of people who don't work at all. And then it's not the case that A works at any company, much less works at the same company as A. So this would be a relation which is not reflexive, right? Because not every person is in here as person, I don't know, my grandmother doesn't work at any company, so she cannot be in this pair, grandmother, because she doesn't work at any company. And is it transitive? If A and B work at the same company and B and C work at the same company, then A and C work at the same company. Yes. So here's an example of a relation which is symmetric, transitive, but not reflexive. Um, let's do another one where we have two of them. So let's look at A and B, the set of all people in people cross people, such that let's do such that A and B have met. So if A and B have met, then have B and A met? Yes, so this is symmetric. I'm going to assume that you know yourself, which is a valid definition I can make. If I say that you know yourself, then it's reflexive because everyone has met themselves. And is it transitive? No, because just because I've met someone and they've met someone else doesn't mean that I've met someone else, right? So here's an example of a relation which is symmetric and reflexive but not transitive. All right, we've got two more. One relation which is only symmetric and one relation which is only reflexive. So let's do um, the following relation, A and B in R cross R, such that A is equal to negative B. Okay, so you take some number and then you take its negative. Question is it symmetric? Well, yes. If I take some number and then the next factor is its negative, then if I reverse the order, it's still the case that the relationship is you take the first number and the second number is the negative of that, right? If I take 3 and negative 3, then it's also the case that negative 3 and 3 satisfies it because 3 is negative of negative 3. So it's symmetric. Is it reflexive? No. There's one element which is reflexive, namely 0, 0, but 1, 1 is not in R because negative 1, because 1 is not negative 1, basically. So 1, 1 is not in R, and for reflexive, I would need every pair AA. For all A and R, I'd need AA to appear in my relation, and that doesn't hold. And it's also not transitive for essentially the same reason. Transitivity says if 3 and negative 3 is in, and negative 3 and 3 is in, transitivity would say that 3, 3 is in the relation. But 3, 3 is not in the relation for the same reason that 1, 1 is not in the relation. So this is a relation that is only symmetric, not reflexive, not transitive. And for the last one, let's have the following relation, AB in, let's say, people cross people. And technically for this, so there's a math example that's more explicit, but here let me do people who are not blind. Cross people who are not blind. And the relation that I want to set up is A has seen B. Okay? So is it symmetric? If A has seen B, does that mean that B has seen A? No, that's not the case. It is possible for me to see someone and for them to never see me. So it's not symmetric. Is it reflexive? This is asking, have you seen yourself? And this is why I restricted our set a little bit so that it would be reflexive. So I'm essentially saying that everyone who can see has seen themselves, which probably already is also not quite true. I don't know. I'm not trying to go too deep on this particular example. So in other words, I can make some modifications such that this is reflexive. And then lastly, it's not transitive, right? Because just because I see someone and they see someone else doesn't mean I've seen someone else. I've probably seen someone who's seen Einstein, but okay, anyways, so here we have a whole interesting list of interesting relations that have some pieces of what is required to be an equivalence relation. Oh, I'm sorry. Okay. But none of these are actually equivalence relations. Now what I want to get to is some actual equivalence relations. Okay. There are a lot of examples of equivalence relations. I just kind of went wild with these not quite examples, but some examples of equivalence relations. One is R is inside R squared such that A minus B, or let me say R is equal to the set of all AB in R squared such that A minus B is an integer. So I'm looking at pairs of real numbers such that their difference is an integer. Okay, let's check. First, is this symmetric? So if A and B is in R, then that means A minus B is in Z. But if A minus B is in Z, then B minus A is in Z, because I can take the negative of an integer and it'll still be an integer. So thus, B comma A is in R. If I take any pair such that their difference is Z, then if I switch it around, this difference is also in Z, in the integers. So it's symmetric. Is it reflexive? Well, yes, because for any real number, AA, since A minus A is equal to 0, which is in Z, 0 is an integer, then AA is in R for all A in R. Sorry, too many R's. This R is for the relation, this R is for the real numbers. And then, is it transitive? So let's assume that A minus B is in Z and B minus C is in Z. Right? This is the condition that, so A, B is in R and BC is in R. And I want to check whether AC is in R. Check if AC is in R. This is checking transitivity. But what I can do is I can just examine the following. AC, or AC is in R since A minus C is equal to A minus B plus B minus C, right? A minus C is equal to A minus C plus B minus B, which is equal to A minus B plus B minus C, and this is in Z, and this is in Z. So A minus C is equal to the sum of two integers, so this is in Z. Okay? So these are the checks that I do to ensure that this relation on R squared, or this relation on the real numbers from the real numbers to the real numbers, is an equivalence relation. This is kind of a fun one, and more or less it is the same idea as the next important equivalence relation. So example 2 is we define an equivalence relation called mod M on Z. So this is a subset of Z cross Z. And here so we're going to define this as A is related mod M to B if A is congruent to B mod M. And remember that this means that A minus B is divisible by M. All right? So essentially what I'm telling you here is that all the work that we did last week when we were talking about congruence of integers modulo M, that's setting up an equivalence relation on Z. So let's check. First of all, let's check that it's symmetric. So if A is congruent to B mod M, so this is the same thing as A comma B being inside R, where the relation is called mod M. If A is congruent to B mod M, then a minus b is equal to m times k, right? This is what it means for a minus b to be divisible by m. It's equal to m times some integer. But if a minus b is equal to m times k, then b minus a, well, that's the negative of this, is just equal to m times negative k. So b minus a is also divisible by m because it's also equal to m times some integer. And you just take the negative of the one that you took up here. Thus, b is congruent to a mod m. And this gives me that congruence is symmetric. Part 2 is we need to show that congruence is reflexive. So show that A is in R for all A and Z. And this is true as well because A minus A is equal to 0 and M divides 0, right? 0 is equal to M times 0. So all integers are in the same relation. All integers are congruent to themselves. And third is transitivity. So let's assume A is congruent to B mod M and B is congruent to C mod M. And what I want to show is that A is congruent to C mod M. Show A is congruent to C mod M. So what I know is that A minus B is equal to mk1, right? And then B minus C is equal to m times k2. So now I want to write A minus C, right? If A minus C is divisible by m, then I'm done, right? I want to show that A is congruent to C mod m, which is the same thing as showing that A minus C is divisible by m. Well, here I can rewrite C is equal to B minus mk, 2, right? So A minus C is equal to A minus B, or minus B minus mk2. So this is equal to A minus B plus mk2. But A minus B is already equal to mk1. So this is equal to mk1 plus mk2, which is equal to m times k1 plus k2, which shows that A minus C is divisible by m. A minus C can be written as m times some integer. Thus, congruence mod m is an equivalence relation. Notice that the two examples that I've given you for an equivalence relation are pretty much the same idea. So the first equivalence relation said that two integers, or two numbers in the real numbers, are equivalent if their difference is an integer. What does it mean for two? Let's kind of examine what is going on there. Let's say that this is 0, this is 1, this is 2, and this is -1. So let's look at all the things that are equivalent to some random number that I pick in here. Who cares what number I pick in here? The point is the set of all elements which are equivalent to this number that I chose are all the numbers that I can get to by adding an integer, right? If I add 1 to whatever this number is, then I'll get an equivalent number because the difference of this number and this number is 1. If I subtract 1 from this number, let's call it x. This is x plus 1. here is going to be x minus 1. And you can imagine x plus 2 and so on and so forth. These are going to be all the things that are equivalent to x. And this is very easy to see when I write it out this way, right? X plus 2 minus x is exactly equal to 2. X plus 1 minus x is exactly equal to 1. X minus 1 minus x is exactly equal to negative 1. So it's the set of all things that are some integer distance away from x. Whereas in the modular arithmetic land, if we let this be 1, 2, 0, 1, 2, 3, 4, let's let m be equal to 3. Let's look mod 3. 4, 5, 6. Then if I pick some integer like 2, all the things that are equivalent to 2 modulo 3 are all the things, all the integers that I can reach by taking steps of 3, right? 2 is going to be equivalent to 5, which is going to be equivalent to 6, 7, 8, right? These are all the things that I can get by moving by 3, right? 2 and 5 have the same remainder when they're divided by 3. 2 and 8 have the same remainder when divided by 3, etc. So these are the two examples that I've given are really the same idea. Okay, let's see what to do next. So let's continue with another definition. So let R be an equivalence relation on A. So the set of all elements that are related to A is called an equivalence class of A. The set of all elements equivalent to little a in A is an equivalence class, or the equivalence class of little a. So this is written by A, so more set theoretically, I could write the class of A is equal to the set of all S in A such that A is related to S under the relation R. Okay. The elements in this set are called representatives. So in particular, if I'm looking at mod 3, the equivalence class of 2 is the set of all integers that have remainder 2 when divided by 3, and some representatives of the class 2. A representative would be 5, a representative would be 8, a representative would be negative 1, right? These would all be representatives of this class. So if S is related to A, then S is a representative of A, where here this box notes the equivalence class of A. So S is a representative of the equivalence class of, right, the equivalence class of A. So this thing is the equivalence class of A. It's the set of all things that are equivalent to A under the relation. Right. So if you look back at the lecture that I did on a modular arithmetic, when I wrote down those sets of numbers, like I think I was doing equivalence mod 7, and I had these sets that looked like 0, 7, 14, 21, etc. And then I had sets that looked like 1, 6, no, not 6, 1, 8, 15, all the way on and so forth. Those were actually equivalence classes where the relation was congruence modulo 7. I think 7 is what I did. So I was showing you equivalence classes back then, even if we didn't kind of formalize the notion. Okay, so now I want to kind of move into a nice collection of examples, which we'll get into more next time. So maybe I'll kind of only describe what's going on. Another nice example of an equivalence class that's more grounded is like take A to be the set of all students who only have one major. So let's say the set of A is people at UNC. So I'm looking at people at UNC who only have one major. My elements of the set are these dots. These are going to be some people. It's not objectifying. They're just points. Okay. So what I'm going to do is I'm going to label a bunch of people by whatever subject they're taking. So let's say that all these people in here are the people whose only major is math. It should be much smaller than that, but okay. And then let's say these people are those whose only major is French. And let's say these people are the people whose only major is history. And these people are people whose only major is comp sci. And these people are people whose only major is literature. And these people are the people whose only major is music, for instance. Okay? The point is that if I'm taking the set A to be the set of all students who have only one major, and imagine that these were the only majors that were offered at UNC, then this would be a way of breaking up the set A such that oh man, once again, I keep messing up so the point is, this is a way of splitting up the set A such that every element of A, namely every student, is exactly inside one box. Every element of A is inside some unique box which is labeled math or labeled French or labeled music or whatever. So this is getting us closer to the idea of a partition. So this notion where I break up a set into distinct chunks such that every element is inside one of the chunks and no element is inside more than one chunk is what we're going to formalize into a notion of partition. So the idea that we will broach next time, equivalence relations induce partitions on the set A. So equivalence relations on A induce partitions on the set A. And we will get started next time with a theorem which will move us in that direction. All right. That is our beginning introduction to equivalence relations and partitions. Thanks.